Hey guys, welcome back to the third video here. Talking about nuclear fusion and fission in this one. Alrighty. So, there's two types of nuclear decay we're going to talk about, or nuclear reactions. And the first one, we're going to talk about fission. And this is when bigger or heavier nuclei, alright, are divided to form smaller ones. And at least one neutron. Right? The prime example we're going to talk about is neutron captured by uranium. Okay, and so this is an example. U-235. So one of the things is uranium, if you look at the periodic table, it's U-238. U-238 does go nuclear decay, but U-238 is not what we call a fissionable material. Uranium-235 is. So we have to somehow take this neutron, right, and fire a neutron into a sample of enough uranium-235 for the reaction to occur. It's a chain reaction. Pretty sure the textbook has a picture of that. Just flip through it real quick. Make sure. No, it doesn't. It doesn't really have a picture of that. That's okay. I don't know if I have a picture of that either. If you want to Google a picture of it, you could. There's all sorts of pictures where it shows you how 1 goes to 3, then goes to 9, and it's an exponential growth of a reaction. It goes really fast. If you look, all these products, there's lots of different products that can happen. But what's important is you get 3, at least in this case, 3 more neutrons and a lot of energy. If you look, it's 2 times 10 to the 13th joules per mole, which is 2.0 times 10 to the 10th kilojoules per mole. So of course a mole would be 235-ish grams. So for every about 235 grams of U-235, right? Now, it's going to be more mass than that, okay? And we'll talk about that in a second. But that's a lot of energy. And so instead of doing some of the other techniques we use to produce energy for the world, nuclear has a lot, right? So you're looking, 235 grams is half a pound-ish, right? So a little more than half a pound, and it gives you 20 billion kilojoules. That's pretty nice. Okay, so nuclear fission reactors. When we talk about generating electricity, electricity is big right now. Everything's trying to go electric, which they call green, which means that your end user, you're not using a fossil fuel that produces carbon dioxide in the air. There's different ways to get electricity. Coal burning power plants, hydroelectric power plants. All power plants are hot water heaters, basically. Okay? A nuclear power plant is no different. Okay? And so what happens is, if you look at the reactor, I'll zoom in on the reactor. These things in yellow are your uranium or whether it's plutonium or whatever you're using for nuclear fuel. That's your fuel. These rods, these control rods, right? The control rods go into up and down in the reactor to slow down. They absorb neutrons. They slow down the reaction so it doesn't go boom. That's kind of a very important thing. All right. And so what's going on? Well, if you look, there's 3 loops of water. There's the first loop of water right here. Loop number 1. Right, and if you look at loop number 1, as you can see the arrows here, it goes in and it heats other water. So that's the water that goes into the reactor, up and around. All right. The second loop of water here. This is the loop, right? That your hot water, and we can get it hotter than 100 degrees Celsius. Why can we get it hotter than 100 degrees Celsius? As you know from earlier, it's the closed system. We increase the vapor pressure, right? So if it's a pressurized system, kind of like a pressure cooker, it can get hotter than 100 degrees Celsius. So then it can heat the second water, which produces steam that turns, right? All we're doing is ultimately this, is turning a coil around a metal a metal coil, a magnet around a metal coil, and generate electricity. That's all we're doing with the turbines, putting electricity. Okay, and then that steam in number 3 here. 3 is your cooling water to like an outside source. Now, nuclear, we're using nuclear material to heat water to turn the turbine to produce electricity. Coal, you use coal to heat water to turn the turbine to produce electricity. Okay, solar is different, not nearly as efficient. One of the things about nuclear is that there are no emissions. There are no emissions, which is nice. So all these fission reactors are nuclear reactors. They're all that way, no matter what source they use. They need a moderator to slow down, right? So water is also used, which we call normal water is light water. So cadmium or boron or both are used to stop extra neutrons. And you use enriched uranium, which is around 3 to 4% U-235. If you use heavy water in the first cycle of water here in the reactor, it's less absorbent of neutrons, and so you do not require enriched uranium. You can use natural uranium. All right. So the question then begs, why don't we use this at all the time? Why don't we use this all the time? All right. Okay. And so, right, because nuclear reactors can produce more fuel than it uses, right? Typically, plutonium can be prepared from uranium, and so it's nice. Well, plutonium is actually extremely toxic, right? It also there's some dangerous products of it, right? So some of the nuclear waste, what do you do with the nuclear waste? It's a good question, right? Again, I don't have answers for this, and I'm not a nuclear chemist, so I couldn't really go into the details with it, how it's stored or whatnot. All right, and it'd be better if we could get better nuclear. Like, I don't know why we don't put more research into here, right? Solar is great because enough. When my research group in grad school at the time, this is many years ago now, the amount of sunlight that hit Arizona was more than enough to power the United States for the day, right? Each day, and the sun shines each day, right? But the problem with solar is that we can't actually hold it and harvest it as much as we would like to. It's just not as efficient. It's not there yet. Well, one of the problems with nuclear is that there's an accident, and there's been 3 major accidents. What do we do, right? The latest one is Fukushima. That was a natural disaster, an earthquake caused a tsunami, and was that Chernobyl? Well, you can read up on Chernobyl. It was not necessarily a great scenario. Let's just say that. And 3 Mile Island also happened. And if you look, that's in the United States. We don't like to talk about that one, but there was a nuclear accident there too. Okay. And so how do you prevent those? How do we make them a little safer? I mean, they're pretty safe now, right? There's only been 3 nuclear reactions since nuclear reactors have been in place. And I would say one of them was definitely not, it was not avoidable, but we've learned from Fukushima, and I'm sure we're making better and improved safeguards. The other 2 we've learned from probably some good lessons. How do we dispose of the nuclear reactor waste? That's a good question too, right? How do we take care of that? Because that is a problem. We don't want to be exposed and have this going out just into the environment. Fusion, right? Nuclear fusion is small, and this is where the sun, hydrogen bombs, right? This is where you have atoms coming together and producing a lot of energy. One of the reasons we don't use this as nuclear fuel is because they're very high temperature, right? Think about the sun. It's 90 some million miles away, and we can feel its heat. Like, it's very high temperature. Now the sun's huge, right? Way bigger than the Earth, but still, it's there's a lot going on there, right? Very high temperature. And so, for example of nuclear fusion, right, you got deuterium, 21H, plus deuterium, 21H, going to tritium, plus hydrogen, right? And that gives you 6.3 times 10 to negative 13 joules per each atom. Well, as you can probably multiply that by a mole, right? You can start seeing how that gets pretty high in energy pretty quickly. All right, so that's nuclear fusion, nuclear fission, all right? And if we could make nuclear fusion happen at room temperature, that would be a game changer for energy in the world. That would be a game changer. I know people are working on it. I don't know how far or how close we are, but those are that. All right, so that's it. That's all we want to do. Now, one last thing to mention is that there are nuclear medicine areas that we can talk about. Right? And some of these radioactive elements are used for detecting or imaging, right? Bone scans for one. You got all sorts of things that, where these elements can go and where you can now analyze and whatnot. And so if you do want to go into the medical field, this is something that kind of cool for you. But we're not going to, our book doesn't dive much into it, and we're not going to dive much into it. Right, so that's all the lectures. In the next video, we'll do some problems. Have a good one.